meeting. All right, so this is where we've stopped for the part one, and then here's the continuation. So for the next one, we're going to discuss the diode circuit problems in series and parallel circuit. Okay, so we have here an example. We have solve for VO, total current, total resistance, and then the total power. Okay, so as you can see right here, we have here a new graph wherein we have here your VS or voltage source. We have here your first diode, which is a silicon, and then the second diode, which is a germanium, and then an additional here wherein you're going to solve for the voltage output at this node. Okay, and then the resistance or your resistor one or equal to 3K. Okay, so without a further delay, let's now calculate, okay, the VO. So VO is, so in here, if they didn't include or it didn't indicated that solve this one using first approximation, second or third one. So the default one is second approximation. Okay, so you will not account for the bulk resistance anymore, but you will account for the uh, threshold voltage of our diode. Okay, so in here, the first thing that we need to do is whether this one is really conducting a voltage or conducting a current. Okay, so positive to positive, positive to positive, negative to negative, negative to negative. So this graph is a forward bias. So meaning this will allow current to pass through to this diode. So the second thing that you need to do is whether this one is above 0.7 volts or above 1 volt. Okay, because we now have a series of diode wherein it will consume a total of 1 volt. So that is the second thing that you need to consider, because if it's less than 1 volt, then this circuit, even though it's a forward bias, will not allow to pass through a current since it doesn't have enough voltage output, okay, or voltage source. So in here, so it's checked. It is above 1 volts, so more than enough. It's 10 volts. Okay, so once you're done with those two characteristics, so you may now proceed in computing the VO, total current, and then total resistance, and then the total power. Okay, so here's the solution for the number one, example number one. So to solve for the voltage output at this point, okay, we have here your, of course, your voltage source, total voltage, minus the silicon diode, and then the germanium diode, or the first diode or the second diode. So of course, minus VD1 and then minus VD2. So 10 minus 0.7 minus 0.3 is equal to 9 volts. So as at this point, our voltage is 9 volts. Okay. So you don't need to account this one because it didn't pass through this one yet. So in here, at this point, the voltage output is 9 volts. And then for the total current, so I is equal to V divided by R. So your total voltage is 9 volts across this circuit divided by 3K, which is your total resistance. Okay, so if you're going to solve this one, you'll get 3 milliamps or 3 milliampere. And then for the total resistance, so since we only have one resistance, so just write here 3K, 3K ohms. And then for the P total, so if we're talking about the total voltage, so it should be calculated with the voltage source. So you need the total current and then the total voltage. Okay, so total current is 3 milliamps and then the total voltage is 10 volts. So 3 milliamps times 10 volts is 0.03 watts. So there you go. This one is much more simpler than the previous example since you have to calculate everything if it's third approximation or second approximation. Then here by default it's second approximation, and then yeah. So this is the only changes. So instead of power on each component, so we now only need to compute for the total power, which is making it a lot easier. Okay. So question so far regarding with the number one.
Done, sir.
Is it clear? I hope that you guys understand the thought or the idea of this one. If there's a part that you didn't understand, so let me know so we can go back on that one and then we can discuss it again. Okay, so it seems that most of you doesn't have a question, so I hope so. Moving on, let's have here the example number 2. So the same. So for VO, total current, total resistance, but instead of total power, here we're now going to solve the power across R1. Okay, and then we have here a different circuit. So of course our voltage source will be still here, which is now 7. And then we have a parallel connection of diodes. So the other one is germanium and another one is silicon. Okay, which is of course in germanium it will consume 0.3 volts. And then for silicon it will consume 0.7 volts. And then still we're going to get the voltage output at this point. Okay, and then we have here your resistor or resistance, which is 5K. Okay, so without a further delay, let's now show the solution. Oops. Yeah, I just remember before this one, before I show to you the solution, let me just tell this one. So here's the effects of a short circuit. Okay, this one is being shorted. So the symbol for the current is this one. You guys already know this one. So for the R total is 4 kilo ohms. And since you've short circuited this one. And then for the total current is 2.5 milliamps. Okay. So when R1 is shorted, its resistance is voided and subtracted to the total resistance value. So it is simple terms bypass. So as you can see right here, it bypass our R1. Okay, because this one is being shorted. Okay. And then what is the idea behind this one? So remember that current travels the path of least resistance. This is very important. Okay. So current is like a very wise man, wherein, of course, it will pass through the less resistance. Okay, it will not pass through to the high resistance since he doesn't like that one. It's like a blocks to him. It's like this one, a hindrance. Okay, or anything you could say that it's not a good thing. Okay, so this is why when the metal wire was placed before and across R1, the current travels through the metal wire instead of going through R1. So even though R1 is still connected, so we still have that one in our connection to the circuit, it has 2000 ohms, more resistance than the metal wire. So in reality, okay, in real world, this metal wire consumes a very minimum resistance, maybe 0.01 or 0.05. But compared to this one, wherein it will uh, resist a current of 2 kilo ohms, so of course our current will choose this one, which is only 0 point something, okay, and makes it least desirable for the current. Okay? So our current will pass through to the best route. Okay, so in here the best route is crossing this metal wire. So the same idea with the example number 1. Oops, where is the solution for here? Solution for number 1, solution for number 2. Yeah, there you go. So same idea with solution number 2. Okay, so as you can see right here, we have two diodes, wherein this one will consume 0.3 volts, and then the other one will consume 0.7 volts. So the idea here is wherever is the higher voltage outcome or the voltage output of those diodes, that is where our current will pass through. So as you can see right here, it's very obvious. This one will consume 0.3 volts, and then this one will consume 0.7 volts. So again, our current will pass through the least resistance. So it will choose the germanium side. Okay. So in here, instead of having a 6.3 volts, if you pass through silicon, you will get 6.7 volts, okay, which is higher than the other one. So of course, as a current, okay, I will choose this path, okay, since I will have much more energy left, or I have much more electricity left, okay, or I have much more current left after passing this diode or after passing this path, okay. So same idea. So in here, we have your BS minus BT1, okay. So 7 minus 0.3 is 6.7 volts. So that is our voltage voltage output at this point. So not 6.3 but 6.7. Okay. So for the total current, that's V divided by R is equal to 6.7. Okay. Yeah, 6.7 for this one. And then divided by 5T for the total resistance. And then after calculating this one, you will get 1.34 milliamps. And then for the R total, of course, we have here the R1, which is the only one. So let's put here 5 kilo ohms. And then the last one is power across R1. So in here, we need to get the IR1 or the current across R1. And since we only have one path, okay, this one, and then going through here, it's like working like a series circuit. Okay, you can just simply remove this one and make the series since our current will not pass through this silicon diode. Okay, so in here, our current is single or one only, okay, which is the I total, which is 1.34 milliamps. So, oops, why is it 3 milliamps? 6.7, I think something's wrong with this one. Wait, let me check it. IR1 should be the same with this one, 1.34. Where is my calculator? Why is it 3 milliamps? I is equal to V divided by R. Yeah, so correction. Okay, correction. This one should be 1.34 milliamps. Okay, so we have here your IR1, and then for the VR1, we have here the 3 milliamps times 5K. So where this one came from. So remember that the formula for VR1 or voltage across another resistor is current across another resistor, and then the resistance value or the resistor value. So in here we have the same current because it's we only have one path. Okay, so 3 milliamps times 5K, which is the value of the resistance. So let me just recalculate this one. So 1.34 squared times 5K. So in here, you should have an answer of 8.978 milliwatts. Okay, so correction on this one should be 8.978 milliwatts. Okay, so I'll just change this one after our discussion. So let me just write so that I can remember that I have to change this one. Slide 17. Oops. Just wait. Slide 17. PR1. Current 2. 1 point. All right. So again, correction. This one should be 8.978 milliwatts. Okay, so other than that, do you guys have a question or clarification so far? Question, guys, or clarification?
None, sir.
Seems like you guys are talking, but you guys are muted. So turn on your mic so I can hear you. Question or clarification? None.
None, sir.
From Mr. Brass.
None, sir.
None, sir.
All right, so again, there's a correction in this one. All right, so again, the idea for the parallel is just choose wherever is the least resistance. Okay. All right, so moving on, we have here the example number 3. So solve for V sub O, total current, total resistance, and then the power across D1 or the diode. Okay, so in here it's very simple. Just here is circuit. So let me show you the solution. So we have two ways in solving this one. We have using the Ohm's law and then using the KVL. Okay, so for the V sub O of this one, so crossing this R1, so you have to deduct the voltage across R1 and then deduct also the voltage drop of this diode, which is 0.7 volts. And then just put here whatever is the calculated value. So in here, as you can see, Vs minus VR1 minus VT1. Okay, so we have here your Vs, which is 10 volts. And then we have here your VR1. So of course, you need to solve for the uh, total resistance first. Wherein, okay, let's go here for now. V divided by R. So as you can see right here, our total voltage now is 9.3. We've already deducted the voltage drop across this diode. So 10 minus 0.7 is 9.3 divided by, since they are in series, 3K. So our total resistance is 3K plus 4K. So if you're going to solve this one, you'll get 1.33 milliamps. Okay, so now we now know already the value of our current. So now we can continue or we can solve this one. So for the VR1, so you need to get the I1 or the current across through that R1 multiplied to the value of that R1, which is 3K. So 1.33 milliamps times 3K minus VT1, which is 0.7. So minus 0.7. So just do the math, okay, and then you will get 5.31 volts across through this voltage output. Okay, but how about if it's using KVL? So let's say we have a loop here, okay, and then it's clockwise. So 10 or positive 10 minus the voltage drop across this R1 minus 3K times the I, and then minus 0.7, okay, minus 4K multiplied to I, since we only have one current, okay? And then just simplify this one. So 10 minus 0.7 is 9.3 minus 3K and then minus 4K. So since they have both the same signs, so you can add those two. So you'll get negative 7K or minus 7Ki. And then just transfer this one to the other side. So 9.3 equal to 7Ki. So now you can transfer this 7K below the denominator of the 9.3. Okay, or multiply or divide both sides by 7K. So you will get I is equal to 9.3 divided by 7K, which is equal to 1.33 milliamps. We're in just the same with this one using Ohm's law. Okay. And then, of course, once you've got the current on this one, you can now solve for the voltage drop across R1. Okay. And then you will now be able to get the voltage output on this one. And then for the R total, of course, it's the summation of those two resistors, 3K plus 4K, which is 7 k ohms. And then for the power across that diode, so you need to get the IR1 or the current across through this diode, and then the voltage of this diode. So as you can see, our current has only one path, so our I total is the same with IR1. So 1.33 milliamps times the VD1. Oops. VD1. What happened? So again, guys, correction, sorry. Remove this one, okay? Remove this one and then make this 0.7 volts. Since we're solving for the power across diode. So here, this is the solution for the power across R1, okay, or the VR1. So remove this one, make this 0.7. Okay. Slide 19. So VD1 to, all right. So sorry for this one. Again, correction, this one should be 0.7 volts. And then let me just solve this one, 1.33 milliamps times 0.7 volts. So in here, you should get 0.0931 milliwatts. Okay, so 0.0931 milliwatts. Okay, so I will just correct this one later on. Milliwatts. All right. So any questions so far regarding with the solution of number 3?
None,
Aside,
sir.
None, sir.
all right. So moving on, of course, we have here your example number 4. So solve for VO, total current, the current on each diode, and the total resistance. So as you can see right here, we have a parallel connection of silicon diode. So, okay, let's see what will happen. I forgot to mention. So before proceeding on the solutions on the example number 3 and then 4, okay, or example number 3 and number 2, so you guys have to check whether this circuit is conducting a current or no. So check if it's forward bias or reverse bias. And here we have positive to positive and then negative to negative. So this one is a forward bias. For example number 2, so yes, both of those diodes are conducting a current, but then again, we have to choose for the least resistance. Okay, so positive to positive, negative to negative. So this one is a forward bias. And then for the number 4, so let's also check whether this one is a forward bias or no. So positive to positive, and then negative to negative. So this one is also a forward bias. So meaning those diodes will accept current or will conduct current. Okay, so without a further delay, let's now go to the solution. Okay, so as you can see right here, we have here the voltage output is 0.7 volts. So how come that this one is 0.7 volts? So as you may know, let's say consider this one as resistance. And then in parallel, the voltage across resistance is equal, okay, or the same, okay. And then if you're going to take a look on this one, we have here a voltage drop of 0.7. And then if you're going to take a look on this one, all of our voltage will pass through to this silicon diode 1 and the silicon diode 2. And then the remaining voltage output is only the voltage drop, okay, or the voltage of the diode itself, which is 0.7. Okay, so in here, since we have that concept wherein all of the voltage across the parallel is equal with each other, so we could say that the voltage output here is 0.7 volt. Okay, so as simple as that if we have this kind of setup. Okay, and then for the total current, so V divided by R is equal to, so 7.3, since we have to deduct this diode. So take note, only one diode. Okay, you don't need to deduct those two. Okay, so 7.3 divided by 3K. So if you do the math, you will get 2.43 milliamps. And then if you're going to solve for the, let's say, current on each diode, so since both of those diodes are the same, so all we need to do is calculate the total current at this point, okay? And then just divide it by 2. Okay? So 2.43 milliamps is equal to 1.215 milliamps on this diode or on this path. And then for the second one is the same, which is 1.215 milliamps. And then for the R total, it's 3K. Okay. So in here, if we have a parallel connection of 4 diodes, so nothing will change. It's still 0.7 volts for the voltage output. Since we're getting the concept or the idea of the parallel resistance, wherein they have the same voltage output on each parallel connection. Okay. So any questions so far regarding with this one?
None, sir.
Right. So I hope the others doesn't have a question also, meaning you understand it or you fully understand it. Okay, so moving on, we have here the example number 5. And then if you're going to take a look on this one, we now have two voltage source. We have here the positive 12, and then we have here the negative 7. Okay, so why negative 7? So just take a look on the polarity. So positive, and then this one is going to a negative. Okay, so solve for V sub O, total current, and then the total resistance. Okay, so for V sub O, so you can either go to this one and then just get the total voltage across this one and then deduct it with 0.3, which is the across diode, and then deduct it also with the voltage across this R1. Or you can go the other way around, wherein you're going to use this one, okay, entire voltage, but instead of negative, it's now positive. Okay, since this one has a loop or has what's one polarity, okay, of clockwise. So if we go counterclockwise, so instead of negative, so opposing that one will become positive. Okay, so you can plus this one, 5K to this voltage, and then plus 0.7 to this voltage. Wherein you will get the same correct answer. Okay, so let me just show you the solution. So using Ohm's law, we have here the first V sub O, which is this side, and then another V sub O, which is this side. Okay. So first, of course, you have to know what are the things that you need to consider. So V sub 1 minus this voltage drop across the diode, which is VD1, and then the voltage drop across this R1, which is VR1. So 12 minus 0.3 for the germanium, and then negative 2.57 milliamps. So where did we get this one? So calculate for the current first. Okay. So before we proceed here, let's calculate this one, a total current. So as you can see right here, we get the total voltage and then the total current for us to be able to get the total current. Okay, so 12 minus 0.3 minus 0.7 for the second diode, and then minus negative 7 for this one. Okay, and then if you're going to take a look on this one, so 12 minus 0.3 minus 0.7 is 11. Minus minus will become plus. So 11 plus 7 is 18. Divided by the total resistance, wherein our first resistance is 2K and then the second one is 5K. And then if you're going to take a look on this one, so they are in series connection. So all you need to do is add those two resistance. So 2K plus 5K is 7K. So 18 divided by 7K, you will get 2.57 milliamps. Okay. So once we know the current across this circuit, so we can now solve for the V sub O. So for the VR1, it's the IR1 times the resistance value. Wherein our I1 or IR1 is 2.57 milliamps times 2K. So just do the math, okay? 12 minus 0.3 minus this one, you will get 6.56 volts. Okay? So this one is for the side. How about going from here to the top? So we have here your voltage output. So V sub 2, okay, which is this one, plus VR1. So again, we have here a polarity of clockwise. So going against it will become negative or will become the opposite of this one, okay, which is now positive. Okay, plus VR1. Oops, correction. This one should be VR2. Okay, sorry. Plus VR2. Okay, which is this one. Plus VD2. So many correction. Okay, wait. Slide 23. VR2. Okay. And then in VR2, okay, so same concept. You have to get the current across that one. So IR2 times the resistance value, which is 5K. So 2.57 milliamps times 5K plus the diode, which is 0.7. Okay, so just do the math and you will get roughly a value of 6.55. So of course, you can see we have two different answers, but those are just the same. So we could say that the V sub O is approximately 6.55 or 6.56. Okay, or any of those two, or you can just answer 6.5. Okay, so how about using KVL? Okay, so let's say we have a polarity from this one clockwise. So positive 12 minus 0.3 minus the voltage drop across this one. So minus 2K times the current minus 0.7 and then minus 5K times I, or the voltage drop across this resistance, and then minus negative 7 for this voltage source. So just do the math, then you will get 18 and then 7K, so just transfer this one to the other side. So 18 is equal to 7KI. And then you can now uh, divide both sides by 7K. So I is equal to 18 divided by 7K. And then just do the math and you will get 2.57 milliamps, which is the same with our Ohm's law. Okay. So once you're done getting this one, you can now proceed and get the voltage drop across this R1. Sorry. Okay, and then your R total is of course the summation of those two resistances. They are in series connection. Okay, so 2K plus 5K is 7K ohms. Right? Example number 6, solution. All right, so this is the last example already. So example number 6, we have here your V sub 1, V sub 2, and then V sub 3. Okay, so we have three voltage source. And then again, the idea is the higher the voltage input will be the one that we're going to follow. Okay? Because of course, this one has a higher voltage input than the V sub 1. So we cannot have two the same working voltage input. Okay, it will have a conflict on our circuit. So either of those two will be off, and then another one will be on. So if you're going to take a look at this one, both diodes will conduct current since they are in forward bias. But if you're going to get the voltage output on this one, so this one will get or will have a voltage output of 7.3, and then this one will have a voltage of 11.3. So logically thinking, this one has a higher voltage input or voltage output, so this one will be on, and then the other one will be off. Okay, since we have two the same colliding current, so we cannot or we don't want that one in our circuit. So we will off this one and then we will on this one. So for our V sub O, you guys already know that the V sub O is 11.3 volts. Okay, and then for the total current, so we have to include this one. And of course, the total resistance. Okay, so here's the solution. So V sub O is 11.3 volts. And then for the current, we have here the V. Wait, V, why is it only V? V minus VD2. Sorry, again, correction. This one should be V2, okay? It lacks number 2. So V2 minus VD2 minus V sub 3, okay? Divided by the R, which is 5K. So we have here your V2, which is 12, minus 0.7. This is the silicon diode 2. And then V3 is negative 3. So minus negative 3. Okay, so just do the math here. You'll get 11.3, 14.3. So 14.3 volts divided by 5K is 2.86 milliamps. And then for the R total, it's this one only, since we only have one resistance, which is 5K ohms. Okay. Then once you're done with this one, of course, you're going to have a quiz, a total of 30 points. So 10 points for V sub O, 10 points for the total current, and then 10 points for the total resistance. Okay, so I will leave this one to you guys. Just check check this one on the canvas. Okay, so that's it only. We now only have, I think, 40 seconds or 30 seconds. Do you guys have a question so far?
None,
None,
sir.
sir.
Wala,
All
sir.
right. So we will stop right
Answer.
here and then we will What is that? All right. So if you guys don't have a question anymore, or say you have a question in the future, so you feel free to ask me via Facebook. Okay, so just message me and then I'll accommodate you on that one. Okay, so if you don't have a question anymore, so you may now leave and then have uh, happy breakfast.